This figure contains 3 photos. The first is of a jade green mineral chunk with a darkened regions and a matte surface. The second is of a crystalline mineral chunk composed primarily of bright royal blue shiny crystals and some lighter blue crystalline regions. The third is of long red crystals. Figure 19. One-transition metals often form vibrantly colored complexes. The minerals malachite green, azurite blue, and proustite red are some examples. Credit left. Modification of work by James St. John. Credit middle. Modification of work by Stephanie Clifford. Credit right. Modification of work by Terry Wallace. Chapter Outline 19. 1. Occurrence, preparation and properties of transition metals and their compounds 19. 2. Coordination chemistry of transition metals 19. 3. Spectroscopic and magnetic properties of coordination compounds. We have daily contact with many transition metals. Iron occurs everywhere, from the rings in your spiral notebook and the cutlery in your kitchen to automobiles, ships, buildings, and in the hemoglobin in your blood. Titanium is useful in the manufacture of lightweight, durable products such as bicycle frames, artificial hips, and jewelry. Chromium is useful as a protective plating on plumbing fixtures and automotive detailing. In addition to being used in their pure elemental forms, many compounds containing transition metals have numerous other applications. Silver nitrate is used to create mirrors. Zirconium silicate provides friction in automotive brakes, and many important cancer-fighting agents like the drug cisplatin and related species are platinum compounds. The variety of properties exhibited by transition metals is due to their complex valence shells. Unlike most main group metals where one oxidation state is normally observed, the valence shell structure of transition metals means that they usually occur in several different stable oxidation states. In addition, electron transitions in these elements can correspond with absorption of photons in the visible electromagnetic spectrum, leading to colored compounds. Because of these behaviors, transition metals exhibit a rich and fascinating chemistry. Transition metals are defined as those elements that have, or readily form, partially filled d orbitals. As shown in Figure 19.2, the d-block elements in groups 311 are transition elements. The f-block elements, also called inner transition metals, the lanthanides and actinides, also meet this criterion because the d orbital is partially occupied before the f orbitals. The d orbitals fill with the copper family, group 11. For this reason, the next family, group 12, are technically not transition elements. However, the group 12 elements do display some of the same chemical properties and are commonly included in discussions of transition metals. Some chemists do treat the group 12 elements as transition metals. The periodic table of elements is shown. The 18 columns are labeled group, and the 7 rows are labeled period. Below the table to the right is a box labeled color code, with different colors for metals, metalloids, and nonmetals, as well as solids, liquids, and gases. To the left of this box is an enlarged picture of the upper leftmost box on the table. The number 1 is in its upper left-hand corner and is labeled atomic number. The letter H is in the middle in red, indicating that it is a gas. It is labeled symbol. Below that is the number 1. 8, which is labeled atomic mass. Below that is the word hydrogen, which is labeled name. The color of the box indicates that it is a non-metal. Each element will be described in this order: atomic number, name, symbol, whether it is a metal, metalloid, or non-metal, whether it is a solid, liquid, or gas, and atomic mass. Beginning at the top left of the table, or period 1, group 1, is a box containing 1, hydrogen, H, non-metal gas, and 1,8. There is only one other element box in period 1, group 18, which contains 2, helium, He, non-metal gas, and 4,3. Period 2, group 1 contains 3, lithium, Li metal solid, and 694. Group 2 contains 4, beryllium, Be metal solid, and 912. Groups 3 through 12 are skipped and group 13 contains 5, boron B, metalloid solid 1081. Group 14 contains 6, carbon C, non-metal solid and 12, 1. Group 15 contains 7, nitrogen N, non-metal gas and 14, 1. Group 16 contains 8, oxygen O, non-metal gas and 16. Group 17 contains 9, fluorine F, non-metal gas and 19. Group 18 contains 10, neon Ne, non-metal gas and 2018. Period 3 Group 1 contains 11, sodium N, a metal solid and 22, 99. Group 2 contains 12, magnesium Mg, metal solid and 2431. Groups 3 through 12 are skipped again in period 3 and group 13 contains 13, aluminum Al, metal solid, and 26, 98. Group 14 contains 14, silicon Si, metalloid solid and 28, 9. Group 15 contains 15, phosphorus P, non-metal solid and 30, 97. Group 16 contains 16, sulfur S, non-metal solid and 32, 6. Group 17 contains 17, chlorine Cl, non-metal gas and 35, 45. Group 18 contains 18, argon Ar, non-metal gas and 3995. Period 4 Group 1 contains 19, potassium K, metal solid and 3910. Group 2 contains 20, calcium C, a metal solid and 40. 8. Group 3 contains 21, scandium Sc, metal solid and 44, 96. Group 4 contains 22, titanium Ti, metal solid and 47, 87. Group 5 contains 23, vanadium V, metal solid and 5094. Group 6 contains 24, chromium Cr, metal solid and 52. Group 7 contains 25, manganese Mn, metal solid and 54, 94. Group 8 contains 26, iron Fe, metal solid and 55, 85. Group 9 contains 27, cobalt Co, metal solid and 58, 93. Group 10 contains 28, nickel Ni, metal solid and 58, 69. Group 11 contains 29, copper Cu, metal solid and 63, 55. Group 12 contains 30, zinc Zn, metal solid and 65, 38. Group 13 contains 31, gallium G, a metal solid and 69, 72. Group 14 contains 32, germanium Ge, metalloid solid and 72, 63. Group 15 contains 33, arsenic As, metalloid solid and 74, 92. Group 16 contains 34, selenium Se, non-metal solid and 78, 97. Group 17 contains 35, bromine Br, non-metal liquid and 79, 90. Group 18 contains 36, krypton Kr, non-metal gas, and 83, 80. Period 5 Group 1 contains 37, rubidium Rb, metal solid and 85, 47. Group 2 contains 38, strontium Sr, metal solid and 87, 62. Group 3 contains 39, yttrium Y, metal solid and 88, 91. Group 4 contains 40, zirconium Zr, metal solid and 91, 22. Group 5 contains 41, niobium Nb, metal solid and 92, 91. Group 6 contains 42, molybdenum Mo, metal solid and 95, 95. Group 7 contains 43, technetium Tc, metal solid, and 97. Group 8 contains 44, ruthenium Ru, metal solid and 101. Group 9 contains 45, rhodium Rh, metal solid and 102, 9. Group 10 contains 46, palladium Pd, metal solid and 106, 4. Group 11 contains 47, silver Ag, metal solid and 107, 9. Group 12 contains 48, cadmium Cd, metal solid and 112, 4. Group 13 contains 49, indium, In, metal solid and 114, 8. Group 14 contains 50, tin, Sn, metal solid, and 118, 7. Group 15 contains 51, antimony, Sb, metalloid solid and 121, 8. Group 16 contains 52, tellurium, Te, metalloid solid, and 127, 6. Group 17 contains 53, iodine, I non-metal solid and 126, 9. Group 18 contains 54, xenon, Xe, non-metal gas, and 131, 3. Period 6 Group 1 contains 55, cesium, Cs, metal solid and 132, 9. Group 2 contains 56, barium, Be, a metal solid, and 137, 3. Group 3 breaks the pattern. The box has a large arrow pointing to a row of elements below the table with atomic numbers ranging from 5771. In sequential order by atomic number, the first box in this row contains 57, lanthanum, L, a metal solid and 138, 9. To its right the next is 58, cerium, Ce, metal solid, and 141. Next is 59, praseodymium, Pr, metal solid and 149. Next is 60, neodymium, Nd, metal solid and 144, 2. Next is 61, promethium, Pm, metal solid and 145. Next is 62, samarium, Sm, metal solid and 154. Next is 63, europium, Eu, metal solid, and 152, 0. Next is 64, gadolinium, Gd, metal solid and 157, 3. Next is 65, terbium, Tb, metal solid and 158, 9. Next is 66, dysprosium, Dy, metal solid and 162, 5. Next is 67, holmium, Ho, metal solid and 164, 9. Next is 68, erbium, Er, metal solid and 167, 3. Next is 69, thulium, Tm, metal solid and 168, 9. Next is 70, ytterbium, Yb, metal solid and 173, 1. The last in this special row is 71, lutetium, Lu, metal solid and 175, 0. Continuing in period 6, group 4 contains 72, hafnium, Hf, metal solid, and 178, 5. Group 5 contains 73, tantalum, T, a metal solid and 189. Group 6 contains 74, tungsten, W, metal solid and 183. 8. Group 7 contains 75, rhenium, Re, metal solid and 186, 2. Group 8 contains 76, osmium, Os, metal solid and 192. Group 9 contains 77, iridium, Ir, metal solid and 192, 2. Group 10 contains 78, platinum, Pt, metal solid and 195, 1. Group 11 contains 79, gold, Au, metal solid and 197, 0. Group 12 contains 80, mercury, Hg, metal, liquid and 200, 6. Group 13 contains 81, thallium, Tl, metal solid and 204, 4. Group 14 contains 82, lead, Pb, metal solid and 207, 2. Group 15 contains 83, bismuth, Bi, metal solid, and 209, 0. Group 16 contains 84, polonium, Po, metal solid and 209. Group 17 contains 85, astatine, a T, metalloid, solid and 210. Group 18 contains 86, radon, Rn, nonmetal gas and 222. Period 7 Group 1 contains 87, francium, Fr, metal, solid and 223. Group 2 contains 88, radium, Rm, metal, solid and 226. Group 3 breaks the pattern much like what occurs in period 6. A large arrow points from the box in period 7. Group 3, to a special row containing the elements with atomic numbers ranging from 89103, just below the row which contains atomic numbers 5771. In sequential order by atomic number, the first box in this row contains 89, actinium, a C, metal, solid, and 227. To its right, the next is 90, thorium, Th, metal, solid, and 232 0. Next is 91, protactinium, P, a metal, solid, and 231 0. Next is 92, uranium, U, metal, solid, and 238 0. Next is 93, neptunium, Np, metal, solid, and Np. Next is 94, plutonium, Pu, metal, solid, and 244. Next is 95, americium, a M, metal, solid, and 243. Next is 96, curium, Cm, metal, solid, and 247. Next is 97, berkelium, Bk, metal, solid, and 247. Next is 98, californium, Cf, metal, solid, and 251. Next is 99, einsteinium, Es, metal, solid, and 252. Next is 100, fermium, Fm, metal, solid, and 257. Next is 101, mendelevium, Md, metal, solid, and 258. Next is 102, nobelium, No, metal, solid, and 259. The last in this special row is 103, lawrencium, Lr, metal, solid, and 262. Continuing in period 7, group 4 contains 104, rutherfordium, Rf, metal, solid, and 267. Group 5 contains 105, dubnium, Db, metal, solid, and 270. Group 6 contains 106, seaborgium, Sg, metal, solid, and 271. Group 7 contains 107, borium, Bh, metal, solid, and 270. Group 8 contains 108, hassium, Hs, metal, solid, and 277. Group 9 contains 109, meitnerium, Mt, not indicated, solid, and 276. Group 10 contains 110, darmstadtium, Ds, not indicated, solid, and 281. Group 11 contains 111, Röntgenium, Rg, not indicated, solid, and 282. Group 12 contains 112, Copernicium, Cn, metal, liquid, and 285. Group 13 contains 113, ununtrium, UUT, not indicated, solid, and 285. Group 14 contains 114, flerovium, Fl, not indicated, solid, and 289. Group 15 contains 115, ununpentium, UUP, not indicated, solid, and 288. Group 16 contains 116. Livermorium, LV, not indicated, solid, and 293. Group 17 contains 117, ununceptium, UUS, not indicated, solid, and 294. Group 18 contains 118, ununoctium, UUO, not indicated, solid, and 294. Figure 19. 2. The transition metals are located in groups 311 of the periodic table. The inner transition metals are in the 2 rows below the body of the table. The D-block elements are divided into the first transition series, the elements Sc through Cu, the second transition series, the elements Y through Ag, and the third transition series, the element La and the elements HF through O. Actinium Ac is the first member of the fourth transition series, which also includes Rf through Rg. The F-block elements are the elements C through Lu, which constitute the lanthanide series or lanthanoid series, and the elements Th through Lr, which constitute the actinide series or actinoid series. Because lanthanum behaves very much like the lanthanide elements, it is considered a lanthanide element, even though its electron configuration makes it the first member of the third transition series. Similarly, the behavior of actinium means it is part of the actinide series, although its electron configuration makes it the first member of the fourth transition series. Example 19. 1-valence electrons in transition metals. Review how to write electron configurations, covered in the chapter on electronic structure and periodic properties of elements. Recall that for the transition and intertransition metals, it is necessary to remove the s electrons before the d or f electrons. Then, for each ion, give the electron configuration. A cerium, Roman 3, B lead, Roman 2, C T2 plus D, Am3 plus E, Pd2 plus. For the examples that are transition metals, determine to which series they belong. Solution for ions. The s-valence electrons are lost prior to the d or f electrons. A, C3 plus Z4 F1. C3 plus is an intertransition element in the lanthanide series. B, Pb2 plus Z6 is 25D104 F14. The electrons are lost from the p orbital. This is a main group element. C, titanium, Roman 2 R3D2. First transition series. D, americium, Roman 3 Rn5 F6. Actinide. E, palladium, Roman 2 Kr4D8. Second transition series. Check your learning. Give an example of an ion from the first transition series with no d electrons. Answer: V5 plus is one possibility. Other examples include Sc3 plus, T4 plus, Cr6 plus, and Mn7 plus. Chemistry in everyday life. Uses of lanthanides in devices. Lanthanides, elements 5771, are fairly abundant in the Earth's crust, despite their historic characterization as rare earth elements. Thulium, the rarest naturally occurring lanthanoid, is more common in the Earth's crust than silver, 5 times 10⁻⁵% versus 0.79 times 10⁻⁵% by mass. There are 17 rare earth elements, consisting of the 15 lanthanoids plus scandium and yttrium. They are called rare because they were once difficult to extract economically, so it was rare to have a pure sample. Due to similar chemical properties, it is difficult to separate any one lanthanide from the others. However, newer separation methods, such as ion exchange resins similar to those found in home water softeners, make the separation of these elements easier and more economical. Most ores that contain these elements have low concentrations of all the rare earth elements mixed together. The commercial applications of lanthanides are growing rapidly. For example, europium is important in flat screen displays found in computer monitors, cell phones, and televisions. Neodymium is useful in laptop hard drives and in the processes that convert crude oil into gasoline. Figure 19. 3. Holmium is found in dental and medical equipment. In addition, many alternative energy technologies rely heavily on lanthanoids. Neodymium and dysprosium are key components of hybrid vehicle engines and the magnets used in wind turbines. This figure contains two images. Figure A shows a background with approximately half of the background to the upper right covered by a dark blue quarter circle. The remainder of the background is red. On top of this surface are 15 vertical columns of light blue dots, which are evenly spaced with gaps between them approximately equal to the width of the columns. In Figure B, a computer hard drive is shown. It consists of a thin black plastic rectangular frame on which a thin disk with a metallic appearance is placed. A curved gray shape lies outside of this disk in the rectangular frame and is circled in red. This curved shape has a thin, pointed extension that reaches to the surface of the metallic disk. Figure 19.3. A. Europium is used in display screens for televisions, computer monitors, and cell phones. B. Neodymium magnets are commonly found in computer hard drives. Credit B. Modification of work by KUERT Datenrettung/Flickr. As the demand for lanthanide materials has increased faster than supply, prices have also increased. In 2008, dysprosium cost 110/kg. By 2014, the price had increased to 470/kg. Increasing the supply of lanthanoid elements is one of the most significant challenges facing the industries that rely on the optical and magnetic properties of these materials. The transition elements have many properties in common with other metals. They are almost all hard, high-melting solids that conduct heat and electricity well. They readily form alloys and lose electrons to form stable cations. In addition, transition metals form a wide variety of stable coordination compounds, in which the central metal atom or ion acts as a Lewis acid and accepts one or more pairs of electrons. Many different molecules and ions can donate lone pairs to the metal center, serving as Lewis bases. In this chapter, we shall focus primarily on the chemical behavior of the elements of the first transition series. Properties of the transition elements. Transition metals demonstrate a wide range of chemical behaviors, as can be seen from their reduction potentials. See Appendix H. Some transition metals are strong reducing agents, whereas others have very low reactivity. For example, the lanthanides all form stable 3+ aqueous cations. The driving force for such oxidations is similar to that of alkaline earth metals such as B or Mg, forming B2+ and Mg2+. On the other hand, materials like platinum and gold have much higher reduction potentials. Their ability to resist oxidation makes them useful materials for constructing circuits and jewelry. Ions of the lighter D-block elements, such as Cr3+, Fe3+, and Co2+, form colorful hydrated ions that are stable in water. However, ions in the period just below these, Mo3+, Ru3+, and Ur2+, are unstable and react readily with oxygen from the air. The majority of simple, water-stable ions formed by the heavier D-block elements are oxyanions such as Mo42- and Re-O4-. Ruthenium, osmium, rhodium, iridium, palladium, and platinum are the platinum metals. With difficulty, they form simple cations that are stable in water, and unlike the earlier elements in the second and third transition series, they do not form stable oxyanions. Both the D and F block elements react with nonmetals to form binary compounds. Heating is often required. These elements react with halogens to form a variety of halides ranging in oxidation state from 1+ to 6+. On heating, oxygen reacts with all of the transition elements except palladium, platinum, silver, and gold. The oxides of these latter metals can be formed using other reactants, but they decompose upon heating. The F-block elements, the elements of Group 3, and the elements of the first transition series, except copper, react with aqueous solutions of acids, forming hydrogen gas and solutions of the corresponding salts. Transition metals can form compounds with a wide range of oxidation states. Some of the observed oxidation states of the elements of the first transition series are shown in Figure 19. 4. As we move from left to right across the first transition series, we see that the number of common oxidation states increases at first to a maximum towards the middle of the table, then decreases. The values in the table are typical values. There are other known values, and it is possible to synthesize new additions. For example, in 2014, researchers were successful in synthesizing a new oxidation state of iridium, 9+. A table is shown with 10 columns and 8 rows. The first row is the header, which shows element symbols with atomic numbers as superscripts to the upper left of the element symbols. The following element symbols and numbers are shown in this manner: SC21, Ti22, V23, Cr24, Mn25, Fe26, Co27, Ni28, Cu29, and Zn30. The second row shows the value 1+ under Cu, the third row shows the value 2+ under V, Cr, Mn, Fe, Co, Ni, Cu, and Zn. The fourth row shows the value 3+ under Sc, TiVCrMnFeConi, and Cu the fifth row shows the value 4 plus under TiVCr and Mn. The sixth row shows the value 5 plus only under V. The seventh row shows the value 6 plus under Cr, Mn, and Fe the eighth row shows the value 7 plus under Mn. Figure 19. Four transition metals of the first transition series can form compounds with varying oxidation states. For the element scandium through manganese, the first half of the first transition series, the highest oxidation state corresponds to the loss of all of the electrons in both the s and d orbitals of their valence shells. The titanium, Roman 4 ion, for example, is formed when the titanium atom loses its 2,3d and 2,4s electrons. These highest oxidation states are the most stable forms of scandium, titanium, and vanadium. However, it is not possible to continue to remove all of the valence electrons from metals as we continue through the series. Iron is known to form oxidation states from 2 plus to 6 plus, with iron, Roman 2, and iron, Roman 3, being the most common. Most of the elements of the first transition series form ions with a charge of 2 plus or 3 plus that are stable in water, although those of the early members of the series can be readily oxidized by air. The elements of the second and third transition series generally are more stable in higher oxidation states than are the elements of the first series. In general, the atomic radius increases down a group, which leads to the ions of the second and third series being larger than are those in the first series. Removing electrons from orbitals that are located farther from the nucleus is easier than removing electrons close to the nucleus. For example, molybdenum and tungsten, members of group 6, are limited mostly to an oxidation state of 6 plus in aqueous solution. Chromium, the lightest member of the group, forms stable Cr3 plus ions in water, and in the absence of air, less stable Cr2 plus ions. The sulfide with the highest oxidation state for chromium is Cr2s3, which contains the Cr3 plus ion. Molybdenum and tungsten form sulfides in which the metals exhibit oxidation states of 4 plus and 6 plus. Example 19. 2. Activity of the transition metals, which is the strongest oxidizing agent in acidic solution. Dichromate ion, which contains chromium Vi, permanganate ion, which contains manganese, Roman 7, or titanium dioxide, which contains titanium, Roman 4. Solution first, we need to look up the reduction half reactions in Appendix L for each oxide in the specified oxidation state. Cr2O 72 minus plus 14H plus 6E minus 2 Cr3 plus 7H2O plus 1. 33 VMnO4 minus plus 8H plus 5E minus Mn2 plus H2O plus 1. 51 V TiO2 plus 4H plus 2E minus Ti2 plus 2 H2O minus 0. 50 V A larger reduction potential means that it is easier to reduce the reactant. Permanganate, with the largest reduction potential, is the strongest oxidizer under these conditions. Dichromate is next, followed by titanium dioxide as the weakest oxidizing agent, the hardest to reduce of this set. Check your learning predict what reaction, if any, will occur between HCl and CoS, and between HBr and PTS. You will need to use the standard reduction potentials from Appendix L answer. Co letter 1D460 plus 2 HCl H2 plus Co Cl2, letter 1D44E letter 1D45E. No reaction because PTS will not be oxidized by H plus preparation of the transition elements ancient civilizations knew about iron, copper, silver, and gold. The time periods in human history known as the Bronze Age and Iron Age mark the advancements in which societies learned to isolate certain metals and use them to make tools and goods. Naturally occurring ores of copper, silver, and gold can contain high concentrations of these metals in elemental form, figure 19.5. Iron, on the other hand, occurs on Earth almost exclusively in oxidized forms, such as rust, Fe2O3. The earliest known iron implements were made from iron meteorites. Surviving iron artifacts dating from approximately 4000 to 2500 BC are rare, but all known examples contain specific alloys of iron and nickel that occur only in extraterrestrial objects, not on Earth. It took thousands of years of technological advances before civilizations developed iron smelting, the ability to extract a pure element from its naturally occurring ores, and for iron tools to become common. Three images are provided. In a smooth chunk of a copper-colored metal with an uneven surface is shown. In B, a dull gold chunk of a metal is shown. This chunk has a rough surface to which smaller chunks appear to be attached. In C, a rust-colored chunk of a solid material with a dull surface is shown. Figure 19. 5 transition metals occur in nature in various forms. Examples include A, a nugget of copper, B, a deposit of gold, and C, an ore containing oxidized iron. Credit a modification of work by HTTP, images of elements, com copper 2, JPG, credit C, modification of work by HTTP, images of elements, com iron ore. JPG. Generally, the transition elements are extracted from minerals found in a variety of ores. However, the ease of their recovery varies widely, depending on the concentration of the element in the ore, the identity of the other elements present, and the difficulty of reducing the element to the free metal. In general, it is not difficult to reduce ions of the D-block elements to the free element. Carbon is a sufficiently strong reducing agent in most cases. However, like the ions of the more active main group metals, ions of the F-block elements must be isolated by electrolysis or by reduction with an active metal such as calcium. We shall discuss the processes used for the isolation of iron, copper, and silver, because these three processes illustrate the principal means of isolating most of the D-block metals. In general, each of these processes involves three principal steps: preliminary treatment, smelting, and refining. Preliminary treatment. In general, there is an initial treatment of the ores to make them suitable for the extraction of the metals. This usually involves crushing or grinding the ore, concentrating the metal-bearing components, and sometimes treating these substances chemically to convert them into compounds that are easier to reduce to the metal. Smelting. The next step is the extraction of the metal in the molten state, a process called smelting, which includes reduction of the metallic compound to the metal. Impurities may be removed by the addition of a compound that forms a slag, a substance with a low melting point that can be readily separated from the molten metal. Refining. The final step in the recovery of a metal is refining the metal. Low boiling metals such as zinc and mercury can be refined by distillation. When fused on an inclined table, low melting metals like tin flow away from higher melting impurities. Electrolysis is another common method for refining metals. Isolation of iron. The early application of iron to the manufacture of tools and weapons was possible because of the wide distribution of iron ores and the ease with which iron compounds in the ores could be reduced by carbon. For a long time, charcoal was the form of carbon used in the reduction process. The production and use of iron became much more widespread about 1620, when coke was introduced as the reducing agent. Coke is a form of carbon formed by heating coal in the absence of air to remove impurities. The first step in the metallurgy of iron is usually roasting the ore, heating the ore in air to remove water, decomposing carbonates into oxides, and converting sulfides into oxides. The oxides are then reduced in a blast furnace that is 8,100 feet high and about 25 feet in diameter, figure 19. 6. In which the roasted ore, coke, and limestone, impure CaCO3, are introduced continuously into the top. Molten iron and slag are withdrawn at the bottom. The entire stock in a furnace may weigh several hundred tons. A diagram of a blast furnace is shown. The furnace has a cylindrical shape that is oriented vertically. A pipe at the lower left side of the figure is shaded yellow and is labeled slag. It connects to an interior chamber. Situated at a level just below this piping on the right side of the figure is another pipe that is shaded orange. It opens at the lower right side of the figure. The orange shaded substance at the bottom of the chamber that matches the contents of the pipe to its right is labeled molten iron. The pipe has an arrow exiting to the right pointing to the label outlet. Just above the slag and molten iron regions is narrower tubing on both the left and right sides of the chamber, which leads slightly up and out from the central chamber to small oval shapes. These shapes are labeled preheated air. The region just above the points of entry of these two pipes or tubes into the chamber is a white region in which small rust-colored chunks of material appear suspended. This region tapers slightly to the bottom of the furnace. The region above has an orange background in which small rust-colored chunks are similarly suspended. This region fills nearly half of the interior of the furnace. Above this region is a gray shaded region. At the very top of the furnace, black line segments indicate directed openings through which small rust-colored chunks of material appear to be entering the furnace from the top. This material is labeled roasted or coke limestone. Exiting the gray shaded interior region to the right is a pipe. An arrow points right, exiting the pipe pointing to the label CO, CO subscript 2, N subscript 2. At the right side of the figure, furnace heights are labeled in order of increasing height between the outlet pipes, followed by temperatures and associated chemical reactions. Just above the pipe labeled outlet, no chemical equation appears right of 5 Ft 1510 degrees C. To the right of 15 Ft 1300 degrees C is the equation C plus O subscript 2 right pointing arrow CO subscript 2. To the right of 25 Ft 1125 degrees C are the two equations CaO plus SiO subscript 2 right pointing arrow SiO subscript 3 and C plus CO subscript 2 right pointing arrow 2CO. To the right of 35 Ft 945 degrees C are the two equations CO subscript 3 right pointing arrow CaO plus CO subscript 2 and C plus CO subscript 2 right pointing arrow 2CO. To the right of 45 Ft 865 degrees C is the equation C plus CO subscript 2 right pointing arrow 2CO. To the right of 55 Ft 525 degrees C is the equation FeO plus CO right pointing arrow Fe plus CO subscript 2. To the right of 65 Ft 410 degrees C is the equation Fe subscript 3 O subscript 4 plus CO right pointing arrow 3 FeO plus CO subscript 2. To the right of 75 Ft 230 degrees C is the equation 3 Fe subscript 2 O subscript 3 plus CO right pointing arrow 2 Fe subscript 3 O subscript 4 plus CO subscript 2. Figure 19. 6. Within a blast furnace, different reactions occur in different temperature zones. Carbon monoxide is generated in the hotter bottom regions and rises upward to reduce the iron oxides to pure iron through a series of reactions that take place in the upper regions. Near the bottom of a furnace are nozzles through which preheated air is blown into the furnace. As soon as the air enters, the coke in the region of the nozzles is oxidized to carbon dioxide with the liberation of a great deal of heat. The hot carbon dioxide passes upward through the overlying layer of white-hot coke, where it is reduced to carbon monoxide. Co2, letter 1D454 plus C, letter 1D4602 Co, letter 1D454. The carbon monoxide serves as the reducing agent in the upper regions of the furnace. The individual reactions are indicated in Figure 19. 6. The iron oxides are reduced in the upper region of the furnace. In the middle region, limestone calcium carbonate decomposes and the resulting calcium oxide combines with silica and silicates in the ore to form slag. The slag is mostly calcium silicate and contains most of the commercially unimportant components of the ore. Ka-O letter 1d460 plus CO2 letter 1d460, Ka-CO3 letter 1d459. Just below the middle of the furnace, the temperature is high enough to melt both the iron and the slag. They collect in layers at the bottom of the furnace. The less dense slag floats on the iron and protects it from oxidation. Several times a day, the slag and molten iron are withdrawn from the furnace. The iron is transferred to casting machines or to a steel-making plant, figure 19.7. This figure shows a photo of molten iron. A bright yellow-orange glow appears just left of center in the figure. Smoke appears to be rising toward the top center of the figure. Just below and to the right, sparks appear to be falling. Figure 19. 7 molten iron is shown being cast as steel. Credit: Clint Budd. Much of the iron produced is refined and converted into steel. Steel is made from iron by removing impurities and adding substances such as manganese, chromium, nickel, tungsten, molybdenum, and vanadium to produce alloys with properties that make the material suitable for specific uses. Most steels also contain small but definite percentages of carbon 0.04% to 5%. However, a large part of the carbon contained in iron must be removed in the manufacture of steel. Otherwise, the excess carbon would make the iron brittle. Link to learning. You can watch an animation of steelmaking that walks you through the process. Isolation of copper. The most important ores of copper contain copper sulfides such as covellite Qs, although copper oxides such as tenorite Qo and copper hydroxycarbonates such as malachite Q2, O2Co3 are sometimes found. In the production of copper metal, the concentrated sulfide ore is roasted to remove part of the sulfur as sulfur dioxide. The remaining mixture, which consists of Q2S, Fe-S, Fe-O, and CO2, is mixed with limestone, which serves as a flux, a material that aids in the removal of impurities, and heated. Molten slag forms as the iron and silica are removed by Lewis acid-base reactions. Ca-CO3 letter 1d460 plus CO2 letter 1d460, Ca-CO3 letter 1d459 plus Co2 letter 1d454. Fe-O letter 1d460 plus CO2 letter 1d460 Fe-CO3 letter 1d459. In these reactions, the silicon dioxide behaves as a Lewis acid, which accepts a pair of electrons from the Lewis base, the oxide ion. Reduction of the Q2S that remains after smelting is accomplished by blowing air through the molten material. The air converts part of the Q2S into Q2O. As soon as copper I oxide is formed, it is reduced by the remaining copper I sulfide to metallic copper. 2 Q2S, letter 1d459, plus 3O2 letter 1d454 2 Q2O, letter 1d459, plus 2 So2, letter 1d454. 2 Q2O, letter 1d459, plus Q2S, letter 1d459, 6 Q, letter 1d459, plus So2, letter 1d454. The copper obtained in this way is called blister copper because of its characteristic appearance, which is due to the air blisters it contains, figure 19. 8. This impure copper is cast into large plates, which are used as anodes in the electrolytic refining of the metal, which is described in the chapter on electrochemistry. This figure shows a large, dull, black, lumpy mass with small, metallic flecks displayed on a clear, colorless, rectangular solid base. Figure 19. 8 blister copper is obtained during the conversion of copper-containing ore into pure copper. Credit: Tortitude/Wikimedia Commons. Isolation of silver. Silver sometimes occurs in large nuggets, figure 19.9, but more frequently in veins and related deposits. At one time, panning was an effective method of isolating both silver and gold nuggets. Due to their low reactivity, these metals and a few others occur in deposits as nuggets. The discovery of platinum was due to Spanish explorers in Central America mistaking platinum nuggets for silver. When the metal is not in the form of nuggets, it is often useful to employ a process called hydrometallurgy to separate silver from its ores. Hydrology involves the separation of a metal from a mixture by first converting it into soluble ions, and then extracting and reducing them to precipitate the pure metal. In the presence of air, alkali metal cyanides readily form the soluble dicyanorgentate, ion, AgCN2-, from silver metal or silver-containing compounds such as Ag2S and AgCl. Representative equations are 4 Ag letter 1 D460 plus 8Cn- letter 1 D44 letter 1 D45E plus O2 letter 1 D454 plus 2H2O letter 1 D4594 AgCN2- letter 1 D44 letter 1 D45E plus 4O- letter 1 D44 letter 1 D45E 2 Ag-Des letter 1 D460 plus 8Cn- letter 1 D44 letter 1 D45E plus O2 letter 1 D454 plus 2H2O letter 1 D4594 AgCN2- letter 1 D44 letter 1 D45E plus 2 letter 1 D460 plus 4O- letter 1 D44 letter 1 D45E AgCl letter 1 D460 plus 2Cn- letter 1 D44 letter 1 D45E AgCN2- letter 1 D44 letter 1 D45E plus Cl- letter 1 D44 letter 1 D45E. This figure contains two images. The first is of a small clump of bronze-colored metal with a very rough, irregular surface. The second shows a layer-like region of silver metal embedded in rock. Figure 19. 9 naturally occurring free silver may be found as nuggets A or in veins B. Credit, a modification of work by Teravolt / Wikimedia Commons. Credit B, modification of work by James St. John. The silver is precipitated from the cyanide solution by the addition of either zinc or iron Roman II ions, which serves as the reducing agent. 2 AgCN2-, letter 1 D44 letter 1 D45E plus Zn letter 1 D4602 Ag letter 1 D460 plus ZnCN42-, letter 1 D44 letter 1 D45E. Example 19. 3. Refining redox. One of the steps for refining silver involves converting silver into dicyanorgenate, ions. 4 Ag letter 1 D460 plus 8Cn- letter 1 D44 letter 1 D45E plus O2 letter 1 D454 plus 2H2O letter 1 D4594 AgCN2- letter 1 D44 letter 1 D45E plus 4O- letter 1 D44 letter 1 D45E. Explain why oxygen must be present to carry out the reaction. Why does the reaction not occur as 4 Ag letter 1 D460 plus 8Cn- letter 1 D44 letter 1 D45E 4 Ag Cn2- letter 1 D44 letter 1 D45E? Solution. The charges as well as the atoms must balance in reactions. The silver atom is being oxidized from the 0 oxidation state to the 1+ state. Whenever something loses electrons, something must also gain electrons be reduced to balance the equation. Oxygen is a good oxidizing agent for these reactions because it can gain electrons to go from the 0 oxidation state to the 2- state. Check your learning. During the refining of iron, carbon must be present in the blast furnace. Why is carbon necessary to convert iron oxide into iron? Answer. The carbon is converted into Co, which is the reducing agent that accepts electrons so that iron, Roman III, can be reduced to iron 0. Transition metal compounds. The bonding in the simple compounds of the transition elements ranges from ionic to covalent. In their lower oxidation states, the transition elements form ionic compounds. In their higher oxidation states, they form covalent compounds or polyatomic ions. The variation in oxidation states exhibited by the transition elements gives these compounds a metal-based, Oxidation reduction chemistry. The chemistry of several classes of compounds containing elements of the transition series follows. Halides. Anhydrous halides of each of the transition elements can be prepared by the direct reaction of the metal with halogens. For example, 2Phe letter 1D460 plus 3Cl2 letter 1D454 2Phe Cl3 letter 1D460. Heating a metal halide with additional metal can be used to form a halide of the metal with a lower oxidation state. Phe letter 1D460 plus 2Phe Cl3 letter 1D460, 3Phe Cl2 letter 1D460. The stoichiometry of the metal halide that results from the reaction of the metal with a halogen is determined by the relative amounts of metal and halogen, and by the strength of the halogen as an oxidizing agent. Generally, fluorine forms fluoride-containing metals in their highest oxidation states. The other halogens may not form analogous compounds. In general, the preparation of stable water solutions of the halides of the metals of the first transition series is by the addition of a hydrohalic acid to carbonates, hydroxides, oxides, or other compounds that contain basic anions. Sample reactions are NiCO3, letter 1D460, plus 2HF, letter 1D44, letter 1D45E, NiF2, letter 1D44, letter 1D45E, plus H2O, letter 1D459, plus CO2, letter 1D454. CO2, letter 1D460, plus 2HBr, letter 1D44, letter 1D45E, CO-Br2, letter 1D44, letter 1D45E, plus 2H2O, letter 1D459. Most of the first transition series metals also dissolve in acids, forming a solution of the salt and hydrogen gas. For example, Cr letter 1D460 plus 2HCl, letter 1D44, letter 1D45E, CrCl2, letter 1D44, letter 1D45E plus H2, letter 1D454. The polarity of bonds with transition metals varies based not only upon the electronegativities of the atoms involved, but also upon the oxidation state of the transition metal. Remember that bond polarity is a continuous spectrum, with electrons being shared evenly, covalent bonds, at one extreme, and electrons being transferred completely, ionic bonds, at the other. No bond is ever 100% ionic, and the degree to which the electrons are evenly distributed determines many properties of the compound. Transition metal halides with low oxidation numbers form more ionic bonds. For example, titanium, Roman 2 chloride and titanium, Roman 3 chloride TiCl2 and TiCl3, have high melting points that are characteristic of ionic compounds, but titanium, Roman 4 chloride TiCl4, is a volatile liquid, consistent with having covalent titanium-chlorine bonds. All halides of the heavier D-block elements have significant covalent characteristics. The covalent behavior of the transition metals with higher oxidation states is exemplified by the reaction of the metal tetrahalides with water. Like covalent silicon tetrachloride, both the titanium and vanadium tetrahalides react with water to give solutions containing the corresponding hydrohalic acids and the metal oxides. CCl4, letter 1D459, plus 2H2O, letter 1D459CO2, letter 1D460, plus 4HCl, letter 1D44, letter 1D45E. TiCl4, letter 1D459, plus 2H2O, letter 1D459 TiO2, letter 1D460, plus 4HCl, letter 1D44, letter 1D45E. Oxides. As with the halides, the nature of bonding in oxides of the transition elements is determined by the oxidation state of the metal. Oxides with low oxidation states tend to be more ionic, whereas those with higher oxidation states are more covalent. These variations in bonding are because the electronegativities of the elements are not fixed values. The electronegativity of an element increases with increasing oxidation state. Transition metals in low oxidation states have lower electronegativity values than oxygen, Therefore, these metal oxides are ionic. Transition metals in very high oxidation states have electronegativity values close to that of oxygen, which leads to these oxides being covalent. The oxides of the first transition series can be prepared by heating the metals in air. These oxides are Sc2O3, TO2, V2O5, Cr2O3, Mn3O4, Fe3O4, Co3O4, NiO, and CuO. Alternatively, these oxides and other oxides, with the metals in different oxidation states, can be produced by heating the corresponding hydroxides, carbonates, or oxalates in an inert atmosphere. Iron Roman II oxide can be prepared by heating iron Roman II oxalate, and cobalt Roman II oxide is produced by heating cobalt Roman II hydroxide. Fe-O4, letter 1d460 Fe-O, letter 1d460, plus Co, letter 1d454, plus Co2, letter 1d454. Co-O2, letter 1d460. Co-O, letter 1d460, plus H-Do, letter 1d454. With the exception of CrO3 and Mn2O7, transition metal oxides are not soluble in water. They can react with acids and, in a few cases, with bases. Overall, oxides of transition metals with the lowest oxidation states are basic and react with acids. The intermediate ones are amphoteric, and the highest oxidation states are primarily acidic. Basic metal oxides at a low oxidation state react with aqueous acids to form solutions of salts and water. Examples include the reaction of cobalt, Roman II oxide accepting protons from nitric acid, and scandium, Roman III oxide accepting protons from hydrochloric acid. Co-O, letter 1d460, plus 2HNO3, letter 1d44, letter 1d45e. Co-No32, letter 1d44, letter 1d45e, plus H2O, letter 1d459. Aceto-O3, letter 1d460, plus 6HCl, letter 1d44, letter 1d45e2, SCCl3, letter 1d44, letter 1d45e, plus 3H2O, letter 1d459. The oxides of metals with oxidation states of 4+ are amphoteric, and most are not soluble in either acids or bases. Vanadium, V, oxide, chromium, Vi oxide, and manganese, Roman VII oxide are acidic. They react with solutions of hydroxides to form salts of the oxyanions Vo43-, CrO42-, and MnO4-. For example, the complete ionic equation for the reaction of chromium, Vi, oxide with a strong base is given by CrO3, letter 1d460, plus 2 Na plus, letter 1d44, letter 1d45e, plus 2O-, letter 1d44, letter 1d45e2 Na plus, letter 1d44, letter 1d45e, plus CrO42-, letter 1d44, letter 1d45e, plus H2O, letter 1d459. Chromium, Vi, oxide, and manganese, Roman VII oxide react with water to form the acids H2CrO4 and HMnO4, respectively. Hydroxides. When a soluble hydroxide is added to an aqueous solution of a salt of a transition metal of the first transition series, a gelatinous precipitate forms. For example, adding a solution of sodium hydroxide to a solution of cobalt sulfate produces a gelatinous pink or blue precipitate of cobalt, Roman II hydroxide. The net ionic equation is Co2 plus, letter 1d44, letter 1d45e, plus 2O-, letter 1d44, letter 1d45e, Co-O2, letter 1d460. In this and many other cases, these precipitates are hydroxides containing the transition metal ion, hydroxide ions, and water coordinated to the transition metal. In other cases, the precipitates are hydrated oxides composed of the metal ion, oxide ions, and water of hydration. 4 Fe3 plus, letter 1d44, letter 1d45e, plus 6O-, letter 1d44, letter 1d45e, plus NH2O, letter 1d4592 Fe2O3N plus 3H2O, letter 1d460. These substances do not contain hydroxide ions. However, both the hydroxides and the hydrated oxides react with acids to form salts in water. When precipitating a metal from solution, it is necessary to avoid an excess of hydroxide ion, as this may lead to complex ion formation as discussed later in this chapter. The precipitated metal hydroxides can be separated for further processing or for waste disposal. Carbonates. Many of the elements of the first transition series form insoluble carbonates. It is possible to prepare these carbonates by the addition of a soluble carbonate salt to a solution of a transition metal salt. For example, nickel carbonate can be prepared from solutions of nickel nitrate and sodium carbonate according to the following net ionic equation. Ni2 plus, letter 1d44e, letter 1d45e, plus Co32 minus Ni Co3, letter 1d460. The reactions of the transition metal carbonates are similar to those of the active metal carbonates. They react with acids to form metals salts, carbon dioxide, and water. Upon heating, they decompose, forming the transition metal oxides. Other salts. In many respects, the chemical behavior of the elements of the first transition series is very similar to that of the main group metals. In particular, the same types of reactions that are used to prepare salts of the main group metals can be used to prepare simple ionic salts of these elements. A variety of salts can be prepared from metals that are more active than hydrogen by reaction with the corresponding acids. Scandium metal reacts with hydrobromic acid to form a solution of scandium bromide. 2Sc, letter 1d460, plus 6HBr, letter 1d44e, letter 1d45e, 2ScBr3, letter 1d44e, letter 1d45e, plus 3H2, letter 1d454. The common compounds that we have just discussed can also be used to prepare salts. The reactions involved include the reactions of oxides, hydroxides, or carbonates with acids. For example, NiO2, letter 1d460, plus 2H3O plus, letter 1d44e, letter 1d45e, plus 2ClO4 minus, letter 1d44e, letter 1d45e, Ni2 plus, letter 1d44e, letter 1d45e, plus 2ClO4 minus, letter 1d44e, letter 1d45e, plus 4H2O, letter 1d459. Substitution reactions involving soluble salts may be used to prepare insoluble salts. For example, Ba2 plus, letter 1d44e, letter 1d45e, plus 2Cl minus, letter 1d44e, letter 1d45e, plus 2K plus, letter 1d44e, letter 1d45e, plus CrO42 minus, letter 1d44e, letter 1d45e, Ba CrO4, letter 1d460, plus 2K plus, letter 1d44e, letter 1d45e, plus 2Cl minus, letter 1d44e, letter 1d45e. In our discussion of oxides in this section, we have seen that reactions of the covalent oxides of the transition elements with hydroxides form salts that contain oxyanions of the transition elements. How sciences interconnect. High-temperature superconductors. A superconductor is a substance that conducts electricity with no resistance. This lack of resistance means that there is no energy loss during the transmission of electricity. This would lead to a significant reduction in the cost of electricity. Most currently used commercial superconducting materials, such as NB-Ti and NB3SN, do not become superconducting until they are cooled below 23 K minus 250 degrees C. This requires the use of liquid helium, which has a boiling temperature of 4 K and is expensive and difficult to handle. The cost of liquid helium has deterred the widespread application of superconductors. One of the most exciting scientific discoveries of the 1980s was the characterization of compounds that exhibit superconductivity at temperatures above 90 K. Compared to liquid helium, 90 K is a high temperature. Typical among the high-temperature superconducting materials are oxides containing yttrium, or one of several rare earth elements, barium and copper in a 1:2:3 ratio. The formula of the ionic yttrium compound is Audiobook 307. The new materials become superconducting at temperatures close to 90 K, figure 19. 10. Temperatures that can be reached by cooling with liquid nitrogen, boiling temperature of 77 K. Not only are liquid nitrogen-cooled materials easier to handle, but the cooling costs are also about 1,000 times lower than for liquid helium. Further advances during the same period included materials that became superconducting at even higher temperatures, and with a wider array of materials. The DuPont team, led by Uma Chowdhury and Arthur Slight, identified bismuth-strontium copper oxides that became superconducting at temperatures as high as 110 K, and importantly, did not contain rare earth elements. Advances continued through the subsequent decades until, in 2020, a team led by Ranga Dias at University of Rochester announced the development of a room-temperature superconductor, opening doors to widespread applications. More research and development is needed to realize the potential of these materials, but the possibilities are very promising. A graph is shown. Temperature K appears on the horizontal axis, with axis labels present at 0, 100, 200, and 300. The vertical axis is labeled resistance. This axis begins at 0 and no additional markings are given. The upper end of this axis is terminated with an arrowhead pointing upward, unlike the horizontal axis. From the origin, a red line segment extends right to a point just left of 100 K from this point. The plot continues with a vertical red line segment about 5/6 of the way to the top of the graph. From the top of this line segment, another red line segment extends up and nearly to the top of the graph to the right. Figure 19. 10. The resistance of the high-temperature superconductor Audiobook 307 varies with temperature. Note how the resistance falls to 0 below 92 K when the substance becomes superconducting. Although the brittle, fragile nature of these materials presently hampers their commercial applications, they have tremendous potential that researchers are hard at work improving their processes to help realize. Superconducting transmission lines would carry current for hundreds of miles with no loss of power due to resistance in the wires. This could allow generating stations to be located in areas remote from population centers and near the natural resources necessary for power production. The first project demonstrating the viability of high-temperature superconductor power transmission was established in New York in 2008. Researchers are also working on using this technology to develop other applications, such as smaller and more powerful microchips. In addition, high-temperature superconductors can be used to generate magnetic fields for applications such as medical devices, magnetic levitation trains, and containment fields for nuclear fusion reactors. Figure 19. 11. A photo is shown of a white levitation train on its tracks. A building appears to the right in the background. Figure 19. 11a. This magnetic levitation train, or maglev, uses superconductor technology to move along its tracks. B. A magnet can be levitated using a dish like this as a superconductor. Credit: a modification of work by Alex Needham. Credit B. Modification of work by Kevin Jarrett. Link to learning. Watch how a high-temperature superconductor levitates around a magnetic racetrack in the video. Learning objectives. By the end of this section, you will be able to list the defining traits of coordination compounds, describe the structures of complexes containing monodentate and polydentate ligands, use standard nomenclature rules to name coordination compounds, explain and provide examples of geometric and optical isomerism, identify several natural and technological occurrences of coordination compounds, the hemoglobin in your blood, the chlorophyll in green plants, vitamin B12, and the catalyst used in the manufacture of polyethylene all contain coordination compounds. Ions of the metals, especially the transition metals, are likely to form complexes. Many of these compounds are highly colored, Figure 1912. In the remainder of this chapter, we will consider the structure and bonding of these remarkable compounds. This figure shows 6 containers. Each is filled with a different color liquid. The first appears to be clear, the second appears to be purple, the third appears to be red, the fourth appears to be teal, the fifth appears to be blue, and the sixth also appears to be clear. Figure 19. 12 metal ions that contain partially filled D subshell usually form colored complex ions. Ions with empty D subshell D0 or with filled D subshells D10 usually form colorless complexes. This figure shows, from left to right, solutions containing MH2O, 6N plus ions with M equals SC3 plus D0, Cr3 plus D3, Co2 plus D7, Ni2 plus D8, Cu2 plus D9, and Zn2 plus D10. Credit Saharatwa. Remember that in most main group element compounds, the valence electrons of the isolated atoms combine to form chemical bonds that satisfy the octet rule. For instance, the 4 valence electrons of carbon overlap with electrons from 4 hydrogen atoms to form CH4. The 1 valence electron leaves sodium and adds to the 7 valence electrons of chlorine to form the ionic formula unit NaCl, figure 19. 13. Transition metals do not normally bond in this fashion. They primarily form coordinate covalent bonds, a form of the Lewis acid-base interaction in which both of the electrons in the bond are contributed by a donor Lewis base to an electron acceptor, Lewis acid. The Lewis acid in coordination complexes, often called a central metal ion, or atom, is often a transition metal or inner transition metal, although main group elements can also form coordination compounds. The Lewis base donors, called ligands, can be a wide variety of chemicals, atoms, molecules, or ions. The only requirement is that they have 1 or more electron pairs, which can be donated to the central metal. Most often, this involves a donor atom with a lone pair of electrons that can form a coordinate bond to the metal. 3 electron dot models are shown. To the left, a central C atom is shown with H atoms bonded above, below, to the left, and to the right. Between the C atom and each H atom are 2 electron dots, one red and one black, next to each other in pairs between the atoms. The second structure to the right shows N superscript plus sign followed by a Cl atom in brackets. This Cl atom has pairs of electron dots above, below, left, and right of the element symbol. A single electron dot on the left side of the symbol is shown in red. All others are black. Outside the brackets to the right, a negative sign appears as a superscript. The third structure on the far right has a central Sc atom. This atom is surrounded by 6 pairs of evenly spaced electron dots. These pairs of dots are positioned between the Sc atom and each of the O atoms from 6H subscript 2 O molecules. This entire structure is within brackets to the right of which is the superscript 3+. Figure 1913. A. Covalent bonds involve the sharing of electrons, and ionic bonds involve the transferring of electrons associated with each bonding atom, as indicated by the colored electrons. B. However, coordinate covalent bonds involve electrons from a Lewis base being donated to a metal center. The lone pairs from 6 water molecules form bonds to the scandium ion to form an octahedral complex. Only the donated pairs are shown. The coordination sphere consists of the central metal ion or atom plus its attached ligands. Brackets in a formula enclose the coordination sphere. Species outside the brackets are not part of the coordination sphere. The coordination number of the central metal ion or atom is the number of donor atoms bonded to it. The coordination number for the silver ion in Ag NH3 2+ is 2, figure 19. 14. For the copper Roman 2 ion in CuCl42-, the coordination number is 4, whereas for the cobalt Roman 2 ion in CoH2O, 6,2 plus the coordination number is 6. Each of these ligands is monodentate, from the Greek for one-toothed, meaning that they connect with the central metal through only one atom. In this case, the number of ligands and the coordination number are equal. 3 structures are shown. In a central Ag atom has N atoms bonded to the left and right as indicated by line segments. 3 H atoms are similarly bonded to each N atom extending out and up, out to the side, and out and below each N atom. The structure is enclosed in brackets with a superscript plus sign to the right of the brackets. In B, a Cu atom is at the center of the structure. Line segments indicate bonds to 2 Cl atoms, one above and the other below and to the left of the central atom. To the right, a dashed wedge, narrow toward the Cu atom and widening toward a Cl atom, is shown at the right side of the central Cu atom. A solid wedge is similarly directed toward a Cl atom below and slightly right of the central Cu atom. This structure is enclosed in brackets with a superscript 2 negative sign present to the right of the brackets. In C, a structure is shown with a central CO atom. From the CO atom, line segments indicate bonds to H subscript 2 O molecules above and below the structure. Above and to both the right and left, dashed wedges indicate bonds to 2 H subscript 2 O molecules. Similarly, solid wedges below to both the right and left indicate bonds to 2 more H subscript 2 O molecules. Each bond in this structure is directed toward the O atom in each H subscript 2 O structure. This structure is enclosed in brackets. Outside the brackets to the right is a superscript 2 plus sign. Figure 19. 14. The complexes A, Ag, NH3 2 plus, B, Cu, Cl, 4 2 minus, and C, Co, H2O, 6 2 plus have coordination numbers of 2, 4, and 6, respectively. The geometries of these complexes are the same as we have seen with VSEPR theory for main group elements: linear, tetrahedral, and octahedral. Many other ligands coordinate to the metal in more complex fashions. Bidentate ligands are those in which 2 atoms coordinate to the metal center. For example, ethylene diamine, N, H2CH to CH2NH2, contains 2 nitrogen atoms, each of which has a lone pair and can serve as a Lewis base, figure 19. 15. Both of the atoms can coordinate to a single metal center. In the complex Co, N33+, there are 3 bidentate N ligands, and the coordination number of the cobalt, Roman 3, ion is 6. The most common coordination numbers are 2, 4, and 6, but examples of all coordination numbers from 1 to 15 are known. 2 structures are shown. In a, H subscript 2, N appears at the left end of the structure. A short line segment extends up and to the right from the N atom to a C atom in a CH subscript 2 group. A short line segment extends down and to the right to another C atom in a CH subscript 2 group. A final short line segment extends from this CH subscript 2 group up and to the right to the N atom of an NH subscript 2 group. Each N atom in the structure has a pair of electron dots at its top. In B, a central CO atom has 6 NH subscript 2 groups attached with single bonds. These bonds are indicated with line segments extending above and below, dashed wedges extending up and to the left and right, and solid wedges extending below and to the left and right. The bonds to these groups are all directed toward the N atoms. The NH subscript 2 groups are each connected to C atoms of CH subscript 2 groups, extending outward from the central CO atom. These CH subscript 2 groups are connected in pairs with bonds indicated by short line segments, forming 3 rings in the structure. This entire structure is enclosed in brackets. Outside the brackets to the right is a superscript 3 plus sign. Figure 1915. A. The ethylene diamine N ligand contains 2 atoms with lone pairs that can coordinate to the metal center. B. The cobalt, Roman 3 complex Co N33+, contains 3 of these ligands, each forming 2 bonds to the cobalt ion. Any ligand that bonds to a central metal ion by more than one donor atom is a polydentate ligand, or many teeth, because it can bite into the metal center with more than one bond. The term chelate, pronounced chelate, from the Greek for claw, is also used to describe this type of interaction. Many polydentate ligands are chelating ligands, and a complex consisting of one or more of these ligands and a central metal is a chelate. A chelating ligand is also known as a chelating agent. A chelating ligand holds the metal ion rather like a crab's claw would hold a marble. Figure 19:15 showed one example of a chelate. The heme complex in hemoglobin is another important example. Figure 19:16. It contains a polydentate ligand with 4 donor atoms that coordinate to iron. A structure is shown for the single ligand heme. At the center of this structure is an Fe atom. From this atom, 4 single bonds extend up and to the right and left and below, and to the right and left to 4 N atoms which are shown in red. Each N atom is a component of a 5-member ring with 4 C atoms. Each of these rings has a double bond between the C atoms that are not bonded to the N atom. The C atoms that are bonded to N atoms are connected to C atoms that serve as links between the 5-member rings. The bond to the C atom clockwise from the 5-member ring in each case is a double bond. The bond to the C atom counterclockwise from the 5-member ring in each case is a single bond. To the left of the structure, 2 of the C atoms in the 5-member rings that are not bonded to N are bonded to CH subscript 3 groups. The other carbons in these rings that are not bonded to N atoms are bonded to groups above and below. Above is a CH group double bonded to a CH subscript 2 group. Below is a CH subscript 2 group bonded to another CH subscript 2 group, which is bonded to a CO subscript 2H group. At the right side of the structure, the C atoms in the 5-member rings that are not bonded to N atoms are bonded to additional structures. The C atom to the right in the 5-member ring at the upper right is bonded to a CH group, which is in turn double bonded to a CH subscript 2 group. Similarly, the rightmost C atom from the 5-member ring in the lower right is bonded to a CH subscript 3 group. The C atom from the 5-member ring not bonded to an N atom in the upper right region of the structure is bonded to a CH subscript 3 group above. Similarly, the C atom on the 5-member ring not bonded to an N atom in the lower right region of the structure is bonded to a CH subscript 2 group that is bonded to another CH subscript 2 group, which is bonded to a CO subscript 2H group below. Figure 19:16. The single ligand heme contains 4 nitrogen atoms that coordinate to iron in hemoglobin to form a chelate. Polydentate ligands are sometimes identified with prefixes that indicate the number of donor atoms in the ligand. As we have seen, ligands with one donor atom such as NH3, Cl- and H2O are monodentate ligands. Ligands with 2 donor groups are bidentate ligands. Ethylene-diamine, H2CH to CH2NH2, and the anion of the acid glycine, NH to CH2CO2-. Figure 19:17 are examples of bidentate ligands. Tridentate ligands, tetradentate ligands, pentadentate ligands, and hexadentate ligands contain 3, 4, 5, and 6 donor atoms, respectively. The ligand in heme, figure 19:16, is a tetradentate ligand. A structure is shown. At the center of this structure is an PT atom. From this atom, 2 single bonds extend up and to the right and below, and to the left to 2 O atoms which are shown in red. Similarly, 2 bonds extend up and to the left and down, and to the right to N atoms in NH subscript 2 groups. The N atoms in these groups are in red. The N atoms are bonded to CH subscript 2 groups, which in turn are bonded to C atoms. These C atoms have doubly bonded O atoms bonded and oriented toward the outside of the structure. They are also singly bonded to the O atoms in the structure, forming 2 rings connected by the central PT atom. Figure 19:17 17. Each of the anionic ligands shown attaches in a bidentate fashion to platinum, Roman 2, with both a nitrogen and oxygen atom coordinating to the metal. The naming of complexes. The nomenclature of the complexes is patterned after a system suggested by Alfred Werner, a Swiss chemist and Nobel laureate, whose outstanding work more than 100 years ago laid the foundation for a clearer understanding of these compounds. The following 5 rules are used for naming complexes. If a coordination compound is ionic, name the cation first and the anion second, in accordance with the usual nomenclature. Name the ligands first, followed by the central metal. Name the ligands alphabetically. Negative ligands anions have names formed by adding O to the stem name of the group. For examples, see Table 19. 1. For most neutral ligands, the name of the molecule is used. The 4 common exceptions are aqua H2O, amine NH3, carbonyl CO, and nitrosyl NO. For example, name PT NH3, 2Cl4 as diamine tetrachloroplatinum, Roman 4. Examples of anionic ligands. Anionic ligand name: F-fluoro Cl-chloro Br-bromo, -iodo Cn -cyano, No3 -nitrato, O-hydroxo, O2. Oxocetuo 42 oxalato, Co32 carbonato, Table 19. 1. If more than one ligand of a given type is present, the number is indicated by the prefixes D for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6. Sometimes the prefixes bis for 2, tris for 3, and tetrakis for 4 are used when the name of the ligand already includes D, tri, or tetra, or when the ligand name begins with a vowel. For example, the ion bis, bipyridyl osmium, Roman 2, uses bis to signify that there are 2 ligands attached to O's, and each bipyridyl ligand contains 2 pyridine groups, C5H4N. When the complex is either a cation or a neutral molecule, the name of the central metal atom is spelled exactly like the name of the element, and is followed by a Roman numeral in parentheses to indicate its oxidation state, Table 19. 2 and Table 19.3. When the complex is an anion, the suffix 8 is added to the stem of the name of the metal, followed by the Roman numeral designation of its oxidation state, Table 19.4. Sometimes the Latin name of the metal is used when the English name is clumsy. For example, ferrate is used instead of ironate, plumbate instead leadate, and stannate instead of tinnate. The oxidation state of the metal is determined based on the charges of each ligand and the overall charge of the coordination compound. For example, in Cr, H2O, 4Cl2Br, the coordination sphere in brackets has a charge of 1 plus to balance the bromide ion. The water ligands are neutral, and the chloride ligands are anionic with a charge of 1 minus each. To determine the oxidation state of the metal, we set the overall charge equal to the sum of the ligands and the metal. Plus 1 equals minus 2x, so the oxidation state X is equal to 3 plus. Examples in which the complex is a cation CO, NH3, 6Cl3 hexamine-cobalt, Roman 3, chloride PT, NH3, 4Cl22 plus tetramine-dichloropplatinum, Roman 4, ion Ag NH3 2 plus diamine silver, ion CrH2O, 4Cl2Cl tetraquadichlorochromium, Roman 3, chloride Co H2CH to CH2NH232, so 4,3 tris ethylnediamine, cobalt, Roman 3, sulfate, Table 19. 2 examples in which the complex is neutral PT. NH32Cl4 diamine tetrachloroplatinum, Roman 4 ni H2CH to CH2NH 22Cl2 dichlorobis, ethylnediamine nickel, Roman 2, Table 19. 3 examples in which the complex is an anion PtCl6 minus hexachloroplatinate, Roman 4, ion Na2SnCl6, sodium hexachlorostannate, Roman 4, Table 19. For link to learning, do you think you understand naming coordination complexes? You can look over more examples and test yourself with online quizzes at the University of Sydney's site. Example 19. 4 coordination numbers and oxidation states determine the name of the following complexes and give the coordination number of the central metal atom. A Na 2PtCl6, B K3Fe C2043C Co NH3, 5ClCl2 solution. A. There are 2 Na plus ions, so the coordination sphere has a -2 charge. PtCl6 minus. There are 6 anionic chloride ligands, so -2 equals -6 plus X, and the oxidation state of the platinum is 4 plus. The name of the complex is sodium hexachloroplatinate, Roman 4, and the coordination number is 6. B. The coordination sphere has a charge of 3 minus based on the potassium, and the oxalate ligands each have a charge of 2 minus, so the metal oxidation state is given by -3 equals -6 plus X, and this is an iron Roman 3 complex. The name is potassium trisoxalatoferrate, Roman 3. Note that tris is used instead of tri because the ligand name starts with a vowel. Because oxalate is a bidentate ligand, this complex has a coordination number of 6. See, in this example, the coordination sphere has a cationic charge of 2 plus. The NH3 ligand is neutral, but the chloro ligand has a charge of 1 minus. The oxidation state is found by +2 equals -1 plus X and is 3 plus. So the complex is pentamine chlorocobalt, Roman 3, chloride, and the coordination number is 6. Check your learning. The complex potassium dicyanorgenate, I, is used to make antiseptic compounds. Give the formula and coordination number. Answer: KAgCN2. Coordination number 2. The structures of complexes for transition metal complexes. The coordination number determines the geometry around the central metal ion. The most common structures of the complexes in coordination compounds are square planar, tetrahedral, and octahedral, corresponding to coordination numbers of 4, 4, and 6, respectively. Coordination numbers greater than 6 are less common and yield a variety of structures. See Figure 19, 18, and Table 19. 5. This figure contains 3 diagrams in black and white. The first is labeled pentagonal bipyramid. It has 10 isosceles triangle faces, 5 at the top, joined at a vertex, making a point projecting upward at the top of the figure, and 5 below, joined at a vertex, making a point projecting downward at the base of the figure. The second is labeled square antiprism. It has flat upper and lower square surfaces and sides made up of 8 equilateral triangles. The sides alternate in orientation between pointing up and pointing down. The third diagram is labeled dodecahedron. It has 12 isosceles triangle faces. Figure 19. 18. These are geometries of some complexes with coordination numbers of 7 and 8. Coordination numbers and molecular geometry. Coordination number molecular geometry. Example 2 linear Ag NH3. 2 plus 3 trigonal planar Cu, Cn. 3 2 minus 4 tetrahedral D0 or D10. Low oxidation states for M9. Co 4 4 square planar D8. Ni, Cn, 4 2 minus 5 trigonal bipyramidal Co Cl 5 2 minus 5 square pyramidal Vo, Cn. 4 2 minus 6 octahedral Co Cl 6 3 minus 7 pentagonal bipyramid Zr F7 3 minus 8 square antiprism Re F8 2 minus 8 dodecahedron Mo Cn 8 4 minus 9, and above more complicated structures Re H9 2 minus table 19. 5 unlike main group atoms in which both the bonding and non-bonding electrons determine the molecular shape. The non-bonding d electrons do not change the arrangement of the ligands. Octahedral complexes have a coordination number of 6, and the 6 donor atoms are arranged at the corners of an octahedron around the central metal ion. Examples are shown in Figure 19. 19. The chloride and nitrate anions in Co, H2O, 6Cl2 and Cr, N33, and the potassium cations in K2PtCl6 are outside the brackets and are not bonded to the metal ion. 3 structures are shown. In a structure is shown with a central CO atom. From the CO atom, line segments indicate bonds to H subscript 2O molecules above and below the structure. Above and to both the right and left, dashed wedges indicate bonds to 2 H subscript 2O molecules. Similarly, solid wedges below to both the right and left indicate bonds to 2 more H subscript 2O molecules. Each bond in this structure is directed toward the O atom in each H subscript 2O structure. This structure is enclosed in brackets. Outside the brackets to the right is the superscript 2+. Following this to the right appears 2Cl superscript negative sign. In B, a central Cr atom has 6 NH subscript 2 groups attached with single bonds. These bonds are indicated with line segments extending above and below, dashed wedges extending up and to the left and right, and solid wedges extending below and to the left and right. The bonds to these groups are all directed toward the N atoms. The NH subscript 2 groups are each connected to C atoms of CH subscript 2 groups, extending outward from the central CO atom. These CH subscript 2 groups are connected in pairs with bonds indicated by short line segments. This entire structure is enclosed in brackets. Outside the brackets to the right is the superscript 3+. Following to the right is 3NO subscript 3 superscript negative sign. In C, 2K superscript plus is followed by a structure in brackets. Inside the brackets is a central PT atom. From the PT atom, line segments indicate bonds to Cl atoms above and below the structure. Above and to both the right and left, dashed wedges indicate bonds to Cl atoms. Similarly, solid wedges below to both the right and left indicate bonds to 2 more Cl atoms. This structure is enclosed in brackets. Outside the brackets to the right is the superscript 2 negative sign. Figure 19. 19 Many transition metal complexes adopt octahedral geometries, with 6 donor atoms forming bond angles of 90 degrees about the central atom with adjacent ligands. Note that only ligands within the coordination sphere affect the geometry around the metal center. For transition metals with a coordination number of 4, 2 different geometries are possible: tetrahedral or square planar. Unlike main group elements, where these geometries can be predicted from VSEPR theory, a more detailed discussion of transition metal orbitals, discussed in the section on crystal field theory, is required to predict which complexes will be tetrahedral and which will be square planar. In tetrahedral complexes such as Zn, Cn, 4-2-, figure 1920, each of the ligand pairs forms an angle of 109.5 degrees. In square planar complexes such as Pt, NH3, 2Cl2, each ligand has 2 other ligands at 90 degrees angles called the cis positions, and 1 additional ligand at an 180 degrees angle in the trans position. 2 structures are shown. Inside of brackets, a central Zn atom is bonded to 4 C atoms in a tetrahedral spatial arrangement. Short line segments are used to represent a bond extending above and down and to the left of the Zn atom. A dashed wedge with the vertex at the Zn atom and wide end at the C atom is used to represent a bond down and to the right of the Zn atom. The final bond is indicated by a similar solid wedge again directed down and only slightly right of the center beneath the Zn atom. 4 groups of 3 parallel short line segments are shown indicating triple bonds extending from each C atom opposite the bond with Zn to an associated N atom. Outside the brackets, a superscript of 2 negative is shown. In B, at the center of this structure is a Pt atom. From this atom, a single bond represented by a dashed wedge extends from a vertex at the Pt atom up and to the right to the N atom of an NH subscript 3 group. Similarly, a single bond represented by a solid wedge extends from a vertex at the pt atom down, and to the right to the N atom of an NH subscript 3 group. Another single bond represented by a dashed wedge extends from a vertex at the pt atom up and to the left to a Cl atom. Similarly, a single bond represented by a solid wedge extends from a vertex at the pt atom down and to the left to a Cl atom. Figure 19. 20 transition metals with a coordination number of 4 can adopt a tetrahedral geometry, A as in K2Zn Cn4, or a square planar geometry, B, as shown in PT, NH32Cl2. Isomerism in complexes isomers are different chemical species that have the same chemical formula. Transition metal complexes often exist as geometric isomers, in which the same atoms are connected through the same types of bonds, but with differences in their orientation in space. Coordination complexes with two different ligands in the cis and trans positions from a ligand of interest form isomers. For example, the octahedral Co, NH3, 4Cl2 plus ion has two isomers. In the cis configuration, the two chloride ligands are adjacent to each other, figure 1921. The other isomer, the trans configuration, has the two chloride ligands directly across from one another. Two structures are shown. The first is labeled violet cis form. Below this label inside brackets is a central CO atom. From the CO atom, line segments indicate bonds to a Cl atom above and the O atom of an H subscript 2O group below the structure. Above and to both the right and left, dashed wedges with their vertex at the CO atom widening. As they move out from the atom indicate bonds with O atoms of H subscript 2O groups. Similarly, solid wedges below to both the right and left indicate bonds to a Cl atom on the right and the O atom of an H subscript 2O group on the left. This structure is enclosed in brackets. Outside the brackets to the right is the superscript plus sign. The second is labeled green trans form. Below this label inside brackets is a central CO atom. From the CO atom, line segments indicate bonds to Cl atoms above and below the structure. Above and to both the right and left, dashed wedges indicate bonds with O atoms of H subscript 2O groups. Similarly, solid wedges below to both the right and left indicate bonds to the O atoms of H subscript 2O groups. This structure is also enclosed in brackets with a superscript plus sign outside the brackets to the right. Figure 19. 21. The cis and trans isomers of Co-H2O, 4Cl2+, contain the same ligands attached to the same metal ion, but the spatial arrangement causes these two compounds to have very different properties. Different geometric isomers of a substance are different chemical compounds. They exhibit different properties, even though they have the same formula. For example, the two isomers of Co, NH3, 4Cl2NO3 differ in color. The cis form is violet and the trans form is green. Furthermore, these isomers have different dipole moments, solubilities, and reactivities. As an example of how the arrangement in space can influence the molecular properties, consider the polarity of the two Co, NH3, 4Cl2NO3 isomers. Remember that the polarity of a molecule or ion is determined by the bond dipoles, which are due to the difference in electronegativity of the bonding atoms and their arrangement in space. In one isomer, cis-chloride ligands cause more electron density on one side of the molecule than on the other, making it polar. For the trans isomer, each ligand is directly across from an identical ligand, so the bond dipoles cancel out and the molecule is nonpolar. Example 19. 5 geometric isomers identify which geometric isomer of a PT, NH32Cl2, is shown in figure 19. 20. Draw the other geometric isomer and give its full name. Solution: in the figure 1920, the two chlorine ligands occupy cis positions. The other form is shown in figure 19. 22. When naming specific isomers, the descriptor is listed in front of the name. Therefore, this complex is trans-diamine-dichloroplatinum, Roman 2. A structure is shown with a central PT atom. From this atom, a dashed wedge with its vertex at the PT extends up and to the left toward the Cl atom, indicating a bond and widening as it moves out. Another dashed wedge with its vertex at the PT extends up and to the right toward the NH3 atom, indicating a bond and widening as it moves out. Similarly, a solid wedge below and to the left indicates a bond with an H3N atom, and another solid wedge below and to the right indicates a bond with a Cl atom. Figure 19. 22. The trans isomer of PT, NH3, 2Cl2 has each ligand directly across from an adjacent ligand. Check your learning. Draw the ion trans-diaquatrans-dibromo-trans-dichlorocobalt, Roman 2. Answer: the structure in this figure shows a structure inside brackets. A central CO atom is shown with line segments indicating bonds to Cl atoms above and below the structure. Above and to the left, a dashed wedge with its vertex at the CO atom widening as it moves out from the atom indicates a bond with the O atom of a H subscript 2O group. A second dashed wedge indicates a bond with the central CO atom with a Br atom up and to the right. Similarly, a solid wedge below and to the left indicates a bond with a Br atom. A second solid wedge below and to the right indicates a bond with the O atom of an H subscript 2O group. This structure is enclosed in brackets. Outside the brackets to the right is the superscript 2 negative sign. Another important type of isomers are optical isomers, or enantiomers, in which two objects are exact mirror images of each other but cannot be lined up so that all parts match. This means that optical isomers are non-superimposable mirror images. A classic example of this is a pair of hands, in which the right and left hand are mirror images of one another but cannot be superimposed. Optical isomers are very important in organic and biochemistry because living systems often incorporate one specific optical isomer and not the other. Unlike geometric isomers, pairs of optical isomers have identical properties: boiling point, polarity, solubility, etc. Optical isomers differ only in the way they affect polarized light and how they react with other optical isomers. For coordination complexes, many coordination compounds such as N3N+, in which Mn+ is a central metal ion such as iron Roman 3 or cobalt Roman 2 form enantiomers, as shown in figure 19. 23. These two isomers will react differently with other optical isomers. For example, DNA helices are optical isomers, and the form that occurs in nature right-handed DNA will bind to only one isomer of N3N+, and not the other. Two structures are shown with a vertical dashed line segment between them. The structure left of this line segment has a central M representing a metal atom. To this atom, 6NH subscript 2 groups are attached with single bonds. These bonds are indicated with line segments extending above and below, dashed wedges extending up and to the left and right, and solid wedges extending below and to the left and right. The bonds to these groups are all directed toward the N atoms. The NH subscript 2 groups are each connected to C atoms of CH subscript 2 groups, extending outward from the central M atom. These CH subscript 2 groups are connected in pairs with bonds indicated by short line segments. This structure has the overall appearance of a flower with 3 petals, 2 of which are equidistant from the dashed line. A mirror image of this structure appears on the right side of the dashed line, again with 2 of the petals equidistant from the dashed line to its left. Figure 19. 23. The complex Mn, 3N+, Mn+ equals a metal ion, N equals ethylene diamine, has a non-superimposable mirror image. The Co-N2Cl2+ ion exhibits geometric isomerism, cis-trans, and its cis isomer exists as a pair of optical isomers, figure 1924. This figure includes three structures. The first two are labeled cis-form optical isomers. These structures are followed by a vertical dashed line segment to the right of which appears a third structure that is labeled trans-form. The first structure includes a central CO atom that has 4 NH subscript 2 groups and 2 Cl atoms attached with single bonds. These bonds are indicated with line segments extending above and below, dashed wedges extending up and to the left and right, and solid wedges extending below and to the left and right. Cl atoms are bonded at the top and at the upper left of the structure. The remaining 4 bonds extend from the central CO atom to the N atoms of NH subscript 2 groups. The NH subscript 2 groups are each connected to C atoms of CH subscript 2 groups extending outward from the central CO atom. These CH subscript 2 groups are connected in pairs with bonds indicated by short line segments, forming 2 rings in the structure. This entire structure is enclosed in brackets. Outside the brackets to the right is the superscript plus. The second structure, which appears to be mirror image of the first structure, includes a central CO atom that has 4 NH subscript 2 groups and 2 Cl atoms attached with single bonds. These bonds are indicated with line segments extending above and below, dashed wedges extending up and to the left and right, and solid wedges extending below and to the left and right. Cl atoms are bonded at the top and at the upper right of the structure. The remaining 4 bonds extend from the central CO atom to the N atoms of NH subscript 2 groups. The NH subscript 2 groups are each connected to C atoms of CH subscript 2 groups extending outward from the central CO atom. These CH subscript 2 groups are connected in pairs with bonds indicated by short line segments, forming 2 rings in the structure. This entire structure is enclosed in brackets. Outside the brackets to the right is a superscript plus sign. The third, trans structure includes a central CO atom that has 4 NH subscript 2 groups and 2 Cl atoms attached with single bonds. These bonds are indicated with line segments extending above and below, dashed wedges extending up and to the left and right, and solid wedges extending below and to the left and right. Cl atoms are bonded at the top and bottom of the structure. The remaining 4 bonds extend from the central CO atom to the N atoms of NH subscript 2 groups. The NH subscript 2 groups are each connected to C atoms of CH subscript 2 groups extending outward from the central CO atom. These CH subscript 2 groups are connected in pairs with bonds indicated by short line segments, forming 2 rings in the structure. This entire structure is enclosed in brackets. Outside the brackets to the right is a superscript plus sign. This final structure has rings of atoms on opposite sides of the structure. Figure 19. 24 3 isomeric forms of Co, N2Cl2+ exist. The trans isomer, formed when the chlorines are positioned at a 180 degrees angle, has very different properties from the cis isomers. The mirror images of the cis isomer form a pair of optical isomers, which have identical behavior except when reacting with other enantiomers. Linkage isomers occur when the coordination compound contains a ligand that can bind to the transition metal center through 2 different atoms. For example, the CN ligand can bind through the carbon atom cyano or through the nitrogen atom isocyano. Similarly, SCN- can be bound through the sulfur or nitrogen atom, affording 2 distinct compounds, Co-NH3, 5-SCN2+, or Co-NH3, 5-NCS2+. Ionization isomers, or coordination isomers, occur when one anionic ligand in the inner coordination sphere is replaced with the counter ion from the outer coordination sphere. A simple example of 2 ionization isomers are Co-Cl6Br and Co-Cl5BrCl. Coordination complexes in nature and technology. Chlorophyll, the green pigment in plants, is a complex that contains magnesium, figure 19. 25. This is an example of a main group element in a coordination complex. Plants appear green because chlorophyll absorbs red and purple light. The reflected light consequently appears green. The energy resulting from the absorption of light is used in photosynthesis. Structural formulas are shown for two complex molecules. The first has a central Mg atom, to which N atoms are bonded above, below, left, and right. Each N atom is a component of a five-member ring with four C atoms. Each of these rings has a double bond between the C atoms that are not bonded to the N atom. The C atoms that are bonded to N atoms are connected to C atoms that serve as links between the five-member rings. The bond to the C atom clockwise from the five-member ring in each case is a double bond. The bond to the C atom counterclockwise from the five-member ring in each case is a single bond. To the left of the structure, two of the C atoms in the five-member rings that are not bonded to N atoms are bonded to CH subscript 3 groups. The other carbons in these rings that are not bonded to N atoms are bonded to groups above and below. A variety of groups are attached outside this interconnected system of rings, including four CH subscript 3 groups, a CH subscript 2 CH subscript 2, COOC subscript 20, H subscript 39 group, a CHCH subscript 2 group with a double bond between the C atoms, additional branching to form a five-member carbon ring to which an O atom is double bonded, and a COOCH subscript 3 group is attached. The second structure has a central Cu atom to which four N atoms that participate in five-member rings with C atoms are bonded. Unlike the first molecule, these five-member rings are joined by N atoms between them, with a double bond on the counterclockwise side and a single bond on the clockwise side of each of the four N atoms that link the rings. On the side of each five-member ring opposite its N atom, four additional carbon atoms are bonded, forming six-member carbon rings with alternating double bonds. The double bonds are not present on the bonds that are shared with the five-member rings. Figure 19. 25a. Chlorophyll comes in several different forms, which all have the same basic structure around the magnesium center. B. Copper phthalocyanine blue, a square planar copper complex, is present in some blue dyes. Chemistry in everyday life. Transition metal catalysts. One of the most important applications of transition metals is as industrial catalysts. As you recall from the chapter on kinetics, a catalyst increases the rate of reaction by lowering the activation energy and is regenerated in the catalytic cycle. Over 90% of all manufactured products are made with the aid of one or more catalysts. The ability to bind ligands and change oxidation states makes transition metal catalysts well suited for catalytic applications. Vanadium oxide is used to produce 230 million tons of sulfuric acid worldwide each year, which in turn is used to make everything from fertilizers to cans for food. Plastics are made with the aid of transition metal catalysts, along with detergents, fertilizers, paints, and more. See Figure 19. 26. Very complicated pharmaceuticals are manufactured with catalysts that are selective, reacting with one specific bond out of a large number of possibilities. Catalysts allow processes to be more economical and more environmentally friendly. Developing new catalysts and better understanding of existing systems are important areas of current research. This figure includes 3 photographs. In a photo shows store shelving filled with a variety of brands of laundry detergent. In B, a photo shows a can of yellow paint being stirred. In C, a bag of fertilizer is shown. Figure 19. 26a. Detergents, B. Paints, and C. Fertilizers are all made using transition metal catalysts. Credit A. Modification of work by Mr. Bryan/Flicker. Credit B. Modification of work by Ewan Roberts. Credit C. Modification of work by Osseous/Flicker. Portrait of a chemist Diana D'Alessandro. Dr. Diana D'Alessandro develops new metal-containing materials that demonstrate unique electronic, optical, and magnetic properties. Her research combines the fields of fundamental inorganic and physical chemistry with materials engineering. She is working on many different projects that rely on transition metals. For example, one type of compound she is developing captures carbon dioxide waste from power plants and catalytically converts it into useful products. See Figure 19.27. An image is shown of a catalytic converter. At the upper left, a blue arrow pointing into a pipe that enters a larger, widened chamber is labeled dirty emissions. A small black arrow that points to the lower right is positioned along the upper left side of the widened region. This arrow is labeled additional oxygen from air pump. The image shows the converter with the upper surface removed, exposing a red-brown interior. The portion of the converter closes to the dirty emissions inlet shows small, spherical components in an interior layer. This layer is labeled three-way reduction catalyst. The middle region shows closely packed small brown rods that are aligned parallel to the dirty emissions inlet pipe. The final nearly quarter of the interior of the catalytic converter again shows a layer of closely packed small, red-brown circles. Two large light gray arrows extend from this layer to the open region at the lower right of the image to the label, clean emissions. Figure 19.27 catalytic converters change carbon dioxide emissions from power plants into useful products, and like the one shown here, are also found in cars. Another project involves the development of porous, sponge-like materials that are photoactive. The absorption of light causes the pores of the sponge to change size, allowing gas diffusion to be controlled. This has many potential useful applications, from powering cars with hydrogen fuel cells to making better electronics components. Although not a complex, self-darkening sunglasses are an example of a photoactive substance. Watch this video to learn more about this research and listen to Dr. D'Alessandro, shown in Figure 19.28, describe what it is like being a research chemist. This is a photo of Dr. Diana D'Alessandro. Figure 19.28. Dr. Diana D'Alessandro is a functional materials researcher. Her work combines the inorganic and physical chemistry fields with engineering, working with transition metals to create new systems to power cars and convert energy. Credit. Image courtesy of Diana D'Alessandro. Many other coordination complexes are also brightly colored. The square planar copper, Roman II, complex phthalocyanine blue, from Figure 19.25 is one of many complexes used as pigments or dyes. This complex is used in blue ink, blue jeans, and certain blue paints. The structure of heme, Figure 19.29, the iron-containing complex in hemoglobin, is very similar to that in chlorophyll. In hemoglobin, the red heme complex is bonded to a large protein molecule, globin, by the attachment of the protein to the heme ligand. Oxygen molecules are transported by hemoglobin in the blood by being bound to the iron center. When the hemoglobin loses its oxygen, the color changes to a bluish red. Hemoglobin will only transport oxygen if the iron is Fe2+. Learning objectives by the end of this section, you will be able to outline the basic premise of crystal field theory, CFT, identify molecular geometries associated with various d orbital splitting patterns, predict electron configurations of split d orbitals for selected transition metal atoms or ions, explain spectral and magnetic properties. In terms of CFT, concepts the behavior of coordination compounds cannot be adequately explained by the same theories used for main group element chemistry. The observed geometries of coordination complexes are not consistent with hybridized orbitals on the central metal, overlapping with ligand orbitals, as would be predicted by valence bond theory. The observed colors indicate that the d orbitals often occur at different energy levels rather than all being degenerate, that is, of equal energy, as are the 3p orbitals. To explain the stabilities, structures, colors, and magnetic properties of transition metal complexes, a different bonding model has been developed. Just as valence bond theory explains many aspects of bonding in main group chemistry, crystal field theory is useful in understanding and predicting the behavior of transition metal complexes. Crystal field theory to explain the observed behavior of transition metal complexes, such as how colors arise. A model involving electrostatic interactions between the electrons from the ligand and the electrons in the unhybridized d orbitals of the central metal atom has been developed. This electrostatic model is crystal field theory, CFT. It allows us to understand, interpret, and predict the colors, magnetic behavior, and some structures of coordination compounds of transition metals. CFT focuses on the non-bonding electrons on the central metal ion in coordination complexes, not on the metal-ligand bonds. Like valence bond theory, CFT tells only part of the story of the behavior of complexes. However, it tells the part that valence bond theory does not. In its pure form, CFT ignores any covalent bonding between ligands and metal ions. Both the ligand and the metal are treated as infinitesimally small point charges. All electrons are negative, so the electrons donated from the ligands will repel the electrons of the central metal. Let us consider the behavior of the electrons in the unhybridized d orbitals in an octahedral complex. The 5d orbitals consist of lobe-shaped regions and are arranged in space, as shown in Figure 19.33. In an octahedral complex, the 6 ligands coordinate along the axes. This figure includes diagrams of 5d orbitals. Each diagram includes 3 axes. The z-axis is vertical and is denoted with an upward pointing arrow. It is labeled Z in the first diagram. Arrows similarly identify the x-axis with an arrow pointing from the rear left to the right front, diagonally across the figure, and the y-axis with an arrow pointing from the left front, diagonally across the figure, to the right rear of the diagram. These axes are similarly labeled as x and y in this first diagram. 4 orange balloon-like shapes extend from a point at the origin out along the x and y axes in positive and negative directions, covering just over half the length of the positive and negative x and y axes. Beneath the diagram is the label d subscript x superscript 2 minus y superscript 2. The second diagram just right of the first is similar, except the x, y, and z labels have been replaced in each instance with the letter L. Only a pair of the orange balloon-like shapes are present and extend from the origin above and below along the vertical axis. An orange toroidal or donut shape is positioned around the origin, oriented through the x and y axes. This shape extends out to about a third of the length of the positive and negative regions of the x and y axes. This diagram is labeled d subscript z superscript 2. The third through fifth diagrams, similar to the first, show 4 orange balloon-like shapes. These diagrams differ, however, in the orientation of the shapes along the axes, and the x, y, and z-axis labels have each been replaced with the letter L. Planes are added to the figures to help show the orientation differences with these diagrams. In the third diagram, a green plane is oriented vertically through the length of the x-axis, and a blue plane is oriented horizontally through the length of the y-axis. The balloon shapes extend from the origin to the spaces between the positive z and negative y-axes, positive z and positive y-axes, negative z and negative y-axes, and negative z and positive y-axes. This diagram is labeled d subscript yz. In the fourth diagram, a green plane is oriented vertically through the x and y axes, and a blue plane is oriented horizontally through the length of the x-axis. The balloon shapes extend from the origin to the spaces between the positive z and negative x-axes, positive z and positive x-axes, negative z and negative x-axes, and negative z and positive x-axes. This diagram is labeled d subscript xz. In the fifth diagram, a pink plane is oriented vertically through the length of the y-axis, and a green plane is oriented vertically through the length of the x-axis. The balloon shapes extend from the origin to the spaces between the positive x and negative y-axes, positive x and positive y-axes, negative x and negative y-axes, and negative x and positive y-axes. This diagram is labeled d subscript xy. Figure 19. 33. The directional characteristics of the 5d orbitals are shown here. The shaded portions indicate the phase of the orbitals. The ligands L, coordinate along the axes. For clarity, the ligands have been omitted from the letter 1d451, letter 1d465, 2 minus letter 1d4662 orbital, so that the axis labels could be shown. In an uncomplexed metal ion in the gas phase, the electrons are distributed among the 5d orbitals in accord with Hund's rule, because the orbitals all have the same energy. However, when ligands coordinate to a metal ion, the energies of the d orbitals are no longer the same. In octahedral complexes, the lobes in two of the 5d orbitals, the letter 1d451, letter 1d4672, and letter 1d451, letter 1d465, 2 minus letter 1d4662 orbitals, point toward the ligands, figure 19. 33. These two orbitals are called the for-example orbitals. The symbol actually refers to the symmetry of the orbitals, but we will use it as a convenient name for these two orbitals in an octahedral complex. The other three orbitals, the dxy, dxz, and dis orbitals, have lobes that point between the ligands and are called the T2G orbitals. Again, the symbol really refers to the symmetry of the orbitals. As 6 ligands approach the metal ion along the axes of the octahedron, their point charges repel the electrons in the d orbitals of the metal ion. However, the repulsions between the electrons in the for-example orbitals, the letter 1d451, letter 1d4672, and letter 1d451, letter 1d465, 2 minus letter 1d4662 orbitals, and the ligands are greater than the repulsions between the electrons in the T2G orbitals, the dzy, dxz, and dis orbitals, and the ligands. This is because the lobes of the for-example orbitals point directly at the ligands, whereas the lobes of the T2G orbitals point between them. Thus, electrons in the for-example orbitals of the metal ion in an octahedral complex have higher potential energies than those of electrons in the T2G orbitals. The difference in energy may be represented as shown in figure 19. 34. A diagram is shown with a vertical arrow pointing upward along the height of the diagram at its left side. This arrow is labeled E. To the right of this arrow are 2 rows of squares outlined in yellow. The first row has 3 evenly spaced squares labeled left to right, d subscript xy, d subscript xz, and d subscript yz. The second row is positioned just above the first and includes 2 evenly spaced squares labeled d subscript z superscript 2 and d subscript x superscript 2 minus y superscript 2. At the right end of the diagram, a short horizontal line segment is drawn just right of the lower side of the rightmost square. A double-sided arrow extends from this line segment to a second horizontal line segment directly above the first and right of the lower side of the squares in the second row. The arrow is labeled capital delta subscript oct. The lower horizontal line segment is similarly labeled T subscript 2G orbitals, and the upper line segment is labeled E subscript G orbitals. Figure 19. 34. In octahedral complexes, the for-example orbitals are destabilized, higher in energy, compared to the T2G orbitals, because the ligands interact more strongly with the d orbitals at which they are pointed directly. The difference in energy between the 4 example and the T2G orbitals is called the crystal field splitting and is symbolized by delta oct, where oct stands for octahedral. The magnitude of delta oct depends on many factors, including the nature of the 6 ligands located around the central metal ion, the charge on the metal, and whether the metal is using 3D, 4D, or 5D orbitals. Different ligands produce different crystal field splittings. The increasing crystal field splitting produced by ligands is expressed in the spectrochemical series, a short version of which is given here. Minus right minus 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 mine. A few ligands of the spectrochemical series. In order of increasing field strength of the ligand, minus Br minus Cl minus F minus H2O, NH3, letter 1D452 letter 1D45B. No 2 minus Cn minus in this series. Ligands on the left cause small crystal field splittings and are weak field ligands, whereas those on the right cause larger splittings and are strong field ligands. Thus, the delta oct value for an octahedral complex with iodide ligands, a minus, is much smaller than the delta oct value for the same metal with cyanide ligands, Cn minus. Electrons in the d orbitals follow the aufbau, filling up, principle, which says that the orbitals will be filled to give the lowest total energy, just as in main group chemistry. When 2 electrons occupy the same orbital, the like charges repel each other. The energy needed to pair up 2 electrons in a single orbital is called the pairing energy, P. Electrons will always singly occupy each orbital in a degenerate set before pairing. P is similar in magnitude to delta oct. When electrons fill the d orbitals, the relative magnitudes of delta oct and P determine which orbitals will be occupied. In Phi, Cn, 6,4-, the strong field of 6 cyanide ligands produces a large delta oct. Under these conditions, the electrons require less energy to pair than they require to be excited to the 4 example orbitals delta oct, P. The 6 3d electrons of the Phi2 plus ion pair in the 3 T2G orbitals, figure 1935. Complexes in which the electrons are paired because of the large crystal field splitting are called low-spin complexes because the number of unpaired electrons, spins, is minimized. A diagram is shown with a vertical arrow pointing upward along the height of the diagram at its left side. This arrow is labeled E. To the right of this arrow are several rows of squares outlined in yellow. The first row has 3 linked squares at the lower right side of the diagram labeled FECN, subscript 6, superscript 4 negative sign. Each square contains 2 half arrows, with the left half arrow pointing up and the right half arrow pointing down. A second row is positioned just above and to the left of the first, with the bottom of the squares at a height equal with the top of the squares in the first row. This group is also composed of 3 linked squares. The square to the left contains 2 half arrows, with the left half arrow pointing up and the right half arrow pointing down. The remaining 2 squares in this row only have upward pointing half arrows. At the bottom of the figure, just below this group is the label FEH subscript 2O subscript 6, superscript 2 plus sign. To the left of this row, a third row that includes 5 linked squares is positioned with the lower edge of the squares at a height equal to the tops of the squares in row 2. The square to the left contains 2 half arrows, one up and one down. All other squares in this group contain single upward pointing arrows. At the bottom of the figure beneath this row appears the label FE superscript 2 plus sign no ligands. A fourth row composed of 2 linked squares appears to the right and above the second row. The lower edge of the squares is at a height level with the top of the squares of the third row. Each of these squares contains a single upward pointing half arrow. A fifth row of 2 squares is positioned above and to the right directly above the first row, with the base of the squares positioned at a level equal to the top of the previous row of squares. These squares are empty. At the right of the diagram, a short horizontal line segment is drawn just right of the lower side of the rightmost square of the first row. A double-headed arrow extends from this line segment to a second horizontal line segment directly above the first and right of the lower side of the fifth row of squares. The arrow is labeled low spin large delta subscript oct to the right. The lower horizontal line segment is similarly labeled T subscript 2G, and the upper line segment is labeled E subscript G. To the right of the second and fourth rows, a short horizontal line segment is drawn just right of the lower side of the rightmost square of the second row. A double-headed arrow extends from this line segment to a second horizontal line segment directly above the first and right of the lower side of the fourth row of squares. The arrow is labeled high spin small capital delta subscript oct to the right. The lower horizontal line segment is similarly labeled T subscript 2G, and the upper line segment is labeled E subscript G. Figure 19. 35 iron, Roman II complexes have 6 electrons in the 5d orbitals. In the absence of a crystal field, the orbitals are degenerate. For coordination complexes with strong field ligands such as Phi, Cn, 6,4-, delta oct is greater than P, and the electrons pair in the lower energy T2G orbitals before occupying the 4-example orbitals. With weak field ligands such as H2O, the ligand field splitting is less than the pairing energy, delta oct less than P, so the electrons occupy all d orbitals singly before any pairing occurs. In Phi, H2O, 6,2+, on the other hand, the weak field of the water molecules produces only a small crystal field splitting, delta oct P. Because it requires less energy for the electrons to occupy the 4-example orbitals than to pair together, there will be an electron in each of the 5 3d orbitals before pairing occurs. For the 6d electrons on the iron, Roman II center in Phi, H2O, 6,2+, there will be 1 pair of electrons and 4 unpaired electrons, figure 1935. Complexes such as the Phi, H2O, 6,2+ ion, in which the electrons are unpaired because the crystal field splitting is not large enough to cause them to pair, are called high-spin complexes because the number of unpaired electrons spins is maximized. A similar line of reasoning shows why the Phi, Cn, 6,3- ion is a low-spin complex with only 1 unpaired electron, whereas both the Phi, H2O, 6,3+, and Phi F 6,3- ions are high-spin complexes with 5 unpaired electrons. Example 19. 7 high and low-spin complexes predict the number of unpaired electrons. A K3Cr6, B, Qn2 H2O2Cl2, C Na3Co, No2 solution. The complexes are octahedral. A Cr3+ has a D3 configuration. These electrons will all be unpaired. B, Q2+ is D9, so there will be 1 unpaired electron. C, Co3+ has D6 valence electrons, so the crystal field splitting will determine how many are paired. Nitrite is a strong field ligand, so the complex will be low spin. 6 electrons will go in the T2G orbitals, leaving 0 unpaired. Check your learning. The size of the crystal field splitting only influences the arrangement of electrons when there is a choice between pairing electrons and filling the higher energy orbitals. For which d-electron configurations will there be a difference between high and low spin configurations in octahedral complexes? Answer: D4, D5, D6, and D7. Example 19. 8 CFT. For other geometries, CFT is applicable to molecules in geometries other than octahedral. In octahedral complexes, remember that the lobes of the 4-example set point directly at the ligands. For tetrahedral complexes, the d orbitals remain in place, but now we have only 4 ligands located between the axes, figure 19. 36. None of the orbitals points directly at the tetrahedral ligands. However, the for-example set along the Cartesian axes overlaps with the ligands less than does the T2G set. By analogy with the octahedral case, predict the energy diagram for the d orbitals in a tetrahedral crystal field. To avoid confusion, the octahedral for-example set becomes a tetrahedral E set, and the octahedral T2G set becomes a T2 set. This figure includes a three-dimensional diagram. At the origin appears the letter M. An arrow, labeled Z, at its tip, points upward through the center. An arrow labeled X at its tip points right through the center. A third arrow labeled Y at its tip points through the center from the left front to the right back portion of the diagram. A rectangular prism is drawn in green, extending out approximately 3/4 of the lengths from the origin along the positive and negative X, Y, and Z axes. Small red spheres are positioned at the left upper front, right upper back, right lower front, and left lower back vertices of the prism. Red lines extend from the central M through the prism to these four small red spheres. Figure 19. 36. This diagram shows the orientation of the tetrahedral ligands with respect to the axis system for the orbitals. Solution: since CFT is based on electrostatic repulsion, the orbitals closer to the ligands will be destabilized and raised in energy relative to the other set of orbitals. The splitting is less than for octahedral complexes because the overlap is less, so delta tet is usually small. Delta tet equals 49 delta oct. A diagram is shown with a vertical arrow pointing upward along the height of the diagram at its left side. This arrow is labeled E. To the right of this arrow are two rows of squares outlined in yellow. The first row has two adjacent squares. The second row is positioned just above the first and includes three adjacent squares. At the right side of the diagram, a short horizontal line segment is drawn just right of the lower side of the rightmost square in the first row. A double-headed arrow extends from this line segment to a second horizontal line segment directly above the first and right of the lower side of the squares in the second row. The arrow is labeled small capital delta subscript tet to the right. The lower horizontal line segment is similarly labeled E subscript, and the upper line segment is labeled T subscript 2. Check your learning. Explain how many unpaired electrons a tetrahedral D4 ion will have. Answer: 4. Because delta tet is small, all tetrahedral complexes are high spin, and the electrons go into the T2 orbitals before pairing. The other common geometry is square planar. It is possible to consider a square planar geometry as an octahedral structure with a pair of trans ligands removed. The removed ligands are assumed to be on the z-axis. This changes the distribution of the d orbitals, as orbitals on or near the z-axis become more stable, and those on or near the x or y-axes become less stable. This results in the octahedral T2G, and the for-example set splitting and gives a more complicated pattern, as depicted below. A diagram is shown with 4 rows of vertically oriented rectangles. The lower level has 2 rectangles with a space between them. The rectangle on the left is labeled D subscript XZ below. The rectangle to its right is similarly labeled D subscript YZ. Just above, the second row contains only one rectangle above and between the lower two. This rectangle is labeled D subscript Z squared. Just above, the third row contains only one rectangle directly above. This rectangle is labeled D subscript XZ. Just above, the fourth row contains only one rectangle directly above. This rectangle is labeled D subscript X squared minus Y squared. Magnetic moments of molecules and ions. Experimental evidence of magnetic measurements supports the theory of high and low spin complexes. Remember that molecules such as O2 that contain unpaired electrons are paramagnetic. Paramagnetic substances are attracted to magnetic fields. Many transition metal complexes have unpaired electrons and hence are paramagnetic. Molecules such as N2 and ions such as NUP, a coordination compound of the Cu plus ion, has a D10 configuration, and all the four example orbitals are filled. To excite an electron to a higher level, such as the 4p orbital, photons of very high energy are necessary. This energy corresponds to very short wavelengths in the ultraviolet region of the spectrum. No visible light is absorbed, so the eye sees no change, and the compound appears white or colorless. A solution containing Cu, Cn2-, for example, is colorless. On the other hand, octahedral Cu2+ complexes have a vacancy in the four example orbitals, and electrons can be excited to this level. The wavelength energy of the light absorbed corresponds to the visible part of the spectrum, and Cu2+ complexes are almost always colored: blue, blue-green, violet, or yellow, figure 19. 40. Although CFT successfully describes many properties of coordination complexes, molecular orbital explanations, beyond the introductory scope provided here, are required to understand fully the behavior of coordination complexes. Two photos are shown. Photo on the left shows a small mound of a white crystalline powder on a watch glass. Photo B shows a small mound of a bright blue crystalline powder. Figure 19. 40. A copper I complexes with D10 configurations such as Cu-I tend to be colorless, whereas BD9 copper Roman II complexes such as Cu-No3, 2,5H2O are brightly colored. Previous.